So here we're going to use the trapezoid rule to approximate this integral. This is an integral we can't do with an antiderivative with n equals 4. Okay, so if we're going to go from 0 to pi over 2 with 4 trapezoids, we've got to do the b minus a over n, which is going to be pi over 2 minus 0 over 4, which is pi over 8. All right, so in our formula, the area is going to be approximately pi, we have to do b minus a over 2n, so it's going to be pi over 16 times, and now we have to figure out this at different values. So we're going to start at f of 0, since that's the left-hand side, plus 2 times f of pi over 8, plus 2 times f of 2 pi over 8, or pi over 4, plus 2 times f of 3 pi over 8, plus 2 times f of 4 pi over 8, or pi over 2. And we have reached the right-hand side of our interval. Okay? Although, actually, I should only have 1 for this last term. Okay? So it should just be f of pi over 2. Okay? So now I need to figure this out, which we'll do with the calculator. So let's do that now. First of all, I'm going to create a list with the different angles that we need to use on it. So I'm going to hit second parenthesis to get my curly bracket there, and then I'm going to enter the different angles. So the first one is 0, and then I have pi over 8, comma, and then I had pi over 4, so second pi divided by 4, comma, and then I have 3 pi over 8, 3 pi over 8, comma, and then I have pi over 2. Alright, so there are 4 trapezoids, which means we have the end point and then the 3 points that are shared between them, and then the other end point of that interval. Okay, and I'm going to store that, so I hit STO, store, in list 1. So second 1 is list 1. Okay, so there's our list of all the angles. So now I need to do f of each of those values. Well, my function is the square root of x times cosine of x. Now, when you're using the calculator, if you do something like the square root of a list, it will actually take the square root of each element in the list. And if I then also do the cosine of a list, it will take the cosine of each element in the list. However, when I multiply those two results together, I'm multiplying two lists together, so it will give me a list, and those are all the values of f of 0, f of pi over 8, f of pi over 4 that you can see, and if we scroll over here, there's f of 3 pi over 8, and then finally f of pi over 2. Okay, so now we got to think about what we need to do with that. Well, the first and last one I just need 1 of, but the middle 3 I need to multiply by 2. So I'm going to actually do times another list, and I'm just going to put 1, 2, 2, 2, 1. Okay, and what that'll do is that'll multiply the first and last terms in that list by 1 and the middle 3 by 2. So I do that. And now those are all the terms in this list. Those are all the terms that are in the brackets over here that I eventually have to multiply by pi over 16. Okay, so the last thing I need to do before I can multiply is actually add these together. And to do that, we go second list, come over here to math, and number 5 is the sum. And I'm going to do the sum of the answer, so shift negative sign. Sum of the answer, and in the parentheses I can see now that that adds up to 3.8686 and so on. So my answer now is pi over 16 times 3.8686. Okay? So now we can multiply that. We've got the pi over 16 times 3.8686 times pi divided by 16, and we get 0.7596. Okay? Now, the second warm-up question here, create a slope field for dy dx equals 1 over x. Okay, so here we have a case where we're trying to draw a slope field. Okay, and we notice here that negative, if I tried to plug in a 0 for x, it would be undefined. So I have, if I'm creating a slope field here, I know that at x equals 0, the slope is going to be undefined. Now, one thing that's kind of interesting here is that notice there's no y in the dy dx. So that means that once I find the value of the slope at one value of x, it's going to be that way no matter what y is. So for example, if I plug in x equals 1, well 1 over 1 is 1. Alright, so I have here at 0, 1, it's going to have a slope of 1, slope of 1, slope of 1. It's going to look like that everywhere, okay? If I have 2, alright, there it's going to have a slope of 1/2, so it's going to be a little bit like this, okay? A little bit more flat. Slope of 1/2. And then the bigger x can get, you can kind of anticipate this, the flatter it's going to be. Okay, so, because you're dividing by more. So it's going to approach a horizontal, although it will never actually equal 0. Okay? Now with the negatives, we're going to have a similar idea. If I have -1, -2, -3, I'll have a slope of 1 over -1, so like that, a slope of 1 over -2, a little bit more flat, and a slope of 1 over -3, like that, and it's getting more and more level, but it's going to be that way no matter what the y value is. So if I were to create a slope field like this, and then a little less flat, okay, you may want to pick x values that aren't so close together. You could get a little more drastic of a change. And then a slope of -1, like this, okay? All right, so we could take a guess. Oh, wait. As we think about this, I actually said for x's greater than 0. We missed that. So I can actually ignore everything over here. And now if I were to plot the point 1, 0, and and try to, graph this the best I can, it's going to look something like this. Okay? And I'm going to guess that that looks about like our natural log function, ln of x. Okay, it looks kind of like the parent function we learned last year. And as we'll see later on in the lesson, that actually is what it is. So now what I want to do is I actually want to kind of tie something that we looked at a significant amount in pre-calc honors to what we're doing now. All right? And that is also to bring about one thing that we saw before, where when we were taking the integral of x to a power, it was x to the n plus 1 over n plus 1, but we said that it would not work if n equaled -1. In other words, if we were doing the integral of 1 over x, it's the integral of x to the -1. If we tried to do this using this power rule, it would have been x to the -1 plus 1 over -1 plus 1, which obviously would be x to the 0 over 0, which doesn't work. Okay? So we have to have a different way of handling this. Okay? And that's where the natural log function comes in. Okay? Here's the definition of the natural log function. And basically we're going to examine this kind of in its inverse relationship between the derivative and the integral, okay? Definition of the natural log function is ln of x is the integral from 1 to x of 1 over t dt. Okay? Now, what you see here in this integral is very similar to what that we just looked at recently? The integral from 1 to x of 1 over t dt? Yeah, that second fundamental theorem of calculus, okay? And in fact, if we were to take the derivative of both sides, we would find that the derivative of ln of x is 1 over x.
Isn't that like what it's saying here? Oh wait, I guess I.
Okay? So by the second fundamental theorem of calculus, or the part 2, we have the derivative of natural log of x equals 1 over x. And if we use that kind of inverse relationship between the derivative and the integral, if we were to then take the integral of 1 over x dx, okay, we would have the natural log of, and here's something that we would have to throw in, it would be the absolute value, okay? And that's because in the function 1 over x, x is allowed to be negative numbers, but in the natural log it's not, okay? That's why over here it says that x has to be greater than 0, okay? So it's almost an inverse relationship, as we've seen with our other integrals and derivatives, okay? But that's what we can develop here, all right? And these are 2 rules that we're going to be using over the next couple of lessons, all right? But what I want to look at today, all right, and this just kind of reiterates this, dy dx is 1 over x, okay? And you can see the points, and that is the graph of the natural log of x, okay? But what we're going to focus on here is kind of reminding ourselves a few things about the natural log function, all right? Y equals ln of x. First of all, remember the domain for the natural log is all positive real numbers greater than 0. Okay? There is an asymptote at 0. Okay? So the domain is the real numbers greater than 0. The range is all real numbers, though. The range is all real numbers. This function is continuous over its whole domain. It is increasing over its whole domain, which means its derivative will always be positive. If it's increasing over the whole domain, its derivative will always be positive. And it's 1 to 1. Now 1 to 1, if you remember a function, every x gets mapped to exactly one y value. If it's 1 to 1, then every y is the result of only one x value. Okay? For example, x squared was a function, but you could get 4 from 2 or negative 2. That's not 1 to 1. Okay? And then also, over the entire domain here, this function is concave downward. And what does that tell us? The second derivative is always negative. Okay? The second derivative is always going to be negative, because it's always concave downward. All right? So those are a couple of things, kind of building on previous knowledge of what we knew about the natural log. Let's do a couple of other things as well, okay? First of all, a little bit about the graphs, okay? If I were to graph ln of x, we just saw this. It has an asymptote at 0. But remember, it also always goes through the point 1, 0. And it also goes through the point E1. Okay, because the natural log of E equals 1. All right, so it's going to look like this. Okay? Now, what happens with B? ln of x minus 2. What's the transformation here? 2 units, is it left or right?
Right.
To the right. Okay, horizontal is always the opposite of what it kind of looks like. All right, so it's 2 units to the right. So instead of the asymptote being on the y-axis, the asymptote is here at 2. Instead of hitting at 1, 0, we're hitting at 3, 0. On the x-axis, and instead of E1, it's going to be E plus 2, 1, whatever that equals, 4.718. Okay? E plus 2. We're not going to draw all of these, but let's at least identify what the transformations are, just as review. For C, what's the transformation? 3 to the left. Good. 3 to the left. How about D? ln of x plus 3. It's up 3. Okay? We will draw this one. What's ln of 2x? What's happening here? Okay? It's horizontal and it's shrunken. It's kind of squished together, all right? So that's not going to affect our asymptote. It's still going to be on the y-axis, all right? However, instead of hitting at 1, 0, it's going to be at 1/2, 0. And instead of E1, it's going to be at E over 2, 1. Okay? Okay? And then you have the other transformations as well. F, what happens on F? ln of x minus 1. Yeah, that's going to go down 1. And how about G? Reflect across the x-axis. Good. Reflect across x-axis. Okay. Now, let's quickly review some properties. Okay? Some properties we can use. First of all, ln of 1 is 0. And actually, any log of 1 is 0 because anything to the 0 power is 1. Okay? Except 0. But you can't have a log base 0 anyways. Okay? Then these rules are useful if you remember that logs are exponents. Okay? What do you do when you're multiplying two things together? What do you do to the exponents? You add them. So if you have a log of two things multiplied together, you can rewrite it as the log of the one plus the log of the other. Okay? What do you do when you're raising a power to a power? You multiply the powers together. Okay? Well, that's why when we have ln of something to a power, we can bring that exponent out in front and multiply the log by that number. Okay? And then finally, what do we do when we're dividing? We subtract the exponent. So if you have ln of a quotient, you can write it as ln of the numerator minus ln of the denominator. Okay? Those are the three basic properties. We can use those in a variety of ways, and as you'll see in tomorrow's lesson, it's really useful when we go to take integrals where we have natural log functions inside. Okay? Now, we can also use these properties to help us evaluate different functions if all we know are certain logarithms. So for example, if we know that the ln of 2 is 0.6931 and ln of 3 is about 1.0986, we could approximate the natural log of 0.25. How would we do that? What?
So it's ln 2 minus ln 8. Maybe ln 5.
Okay.
So 0.5.
Let's think about what you just said. You were saying log 0.25 is 2 divided by 8. What else is it?
1 divided by
1 divided by 4. And 1/4 is
ln 1 minus ln
2 to the
Negative. No, 1/4.
2 to the negative 2. Okay? So guess what? I could rewrite this as negative 2 ln of 2. Right? If I can rewrite the logarithm in terms of ones that I know, okay, that's why we couldn't use log of 4. We didn't know what log of 4 is. Okay, we couldn't use a log of 8 because at that point we didn't know what log of 8 is. We would have had to do some more to it. Okay? But here we know what ln of 2 is. It's negative 2 times the 0.6931. So that's going to be a negative 1.3862. Okay? And I could do that with all of these. All right? I could rewrite 24. 24 is 8 times 3. And 8 is 2 to the third power. Well, now I can split that up. I can make that 3 ln of 2 plus ln of 3. Where I see multiplication, I make it 2 logs added together. Where I see an exponent, I bring it out in front as a coefficient. Okay? And then we can substitute in the values we know. 3 times the 0.6931. Plus 1.0986. Okay, and then we can do the arithmetic. All right, 2.0793 plus 1.0986, and that's 3.1779. Okay, so that is natural log of 24. Okay, and we could do that with all of these. All right. I'd rewrite ln of the cube root of 12 as 1/3 ln of 12. And then if I see ln of 12 as 2 times 2 times 4, or 2 times 2 times 3, sorry, I can make that 1/3 times 2 ln of 2, there's my 4, plus the ln of 3. Okay? And then I could plug it in and simplify. Okay? All right. Now, the last couple here, I want to run through in the last couple minutes we have left. This was the other application of those properties that we had, and that was using it to either expand a logarithm into multiple logarithms or condense an expression that has multiple logarithms down into one. Okay? And depending on the context, both of those can be useful. All right? So, for example, how could I rewrite ln of 10/9? Ln of 10 minus ln of 9. Yeah. Okay? What could I do with b? 1/2 times the ln of 3x plus 2. Can I do any more? You don't think so?
Yeah,
What do
you
you guys
can
think?
plus 3 plus
No, it is plus.
What?
It is plus.
ln 3
It
plus
should be
ln.
multiplication.
Okay. If it's addition inside the argument, can't do anything with that. Okay? If it's addition inside the argument, here 3x plus 2, that's as far as we can simplify. And maybe if it was 3x plus 6, I could factor a 3 out and then make ln of 3 plus ln of something else. But only if there was multiplication could I split it into 2 logs added together. Okay? If you see, that's probably the number one thing that people mess up on these, is they'll see that addition, they'll split it into 2 logs added. You can't do that. All right? Let's skip to this one here. How many logs are we going to split this into?
Maybe 1,
3, 2. We could take it one step at a time. All right. Let's take it one step at a time. So we have division. So let's make it ln of x squared plus 3 squared minus ln of x times the cube root of x squared plus 1.
That's cube.
Okay? Yeah, that's the cube root.
X cube and times.
Yeah, that looks a lot like. Okay, so can we do anything with the first one?
You can put a 2.
Yeah, bring the 2 out in front. Okay, what about that second one?
Long x plus
ln x plus, okay, ln, I heard someone say 1/3
No, 2.
ln
Isn't
of x squared plus 1. Can I pull out the square?
No.
No. Because it's not x plus 1 parentheses squared. It's just the x squared plus the 1. Okay? So that's as far as we could simplify it. If you want to distribute the negative, go ahead. The simple way of thinking about this, when you have multiple things here, is anytime you see something in the denominator, you're going to be subtracting it. If it's in the numerator, it's going to be positive. It's going to be added. All right? So I have one factor in the numerator, so I have one positive one. I have two different factors in the denominator, so I'm going to have two negative logs at the end. Okay? All right. Let's do one condensing one. This one looks fun. All right. Let's condense. Start inside the brackets first of all. What can I do? Divide. Okay. So what's that going to look like? ln of
X plus 1.
of what?
X squared plus 1 minus divided by x plus 1 times
Times
x minus 1.
There we go. Anything that you see is negative, that means put it down in the denominator. Okay? And anything that gets put down in the denominator just gets multiplied together down there. Okay? This was positive, so it ends up in the numerator. What do we do with this 3/2? Exponent, okay? So we could rewrite this as ln of x squared plus 1 over x plus 1, x minus 1. And that whole thing is to the 3/2 power. Or we could make it all cubed and put it in a giant square root if we wanted. Okay? Those are the basics. This should be review from last year, but it's good to bring it back to our memory. And tomorrow in the lesson, you'll see how we could use this to do integrals. Okay?